So I'm going to talk about, so this is Professor Maryam Mirzakhani. I mean, I didn't know about her much till she got, like when we came to know that she got her field medal. And then there were pictures with her having her daughter with her. Whenever, if you search online, and for me that was kind of inspiring to see that, you know, like somebody balancing, doing her work and managed to do everything. Of course, we lost her. That's like something a lot we cannot repair. But then even after she is gone, she has been inspiring many of us, you know, to follow the path. So it's a really great honor. And what I'm going to talk about today is to discuss about the origin of the subject called representation theory of finite groups. So I work in this subject called representation theory of finite groups. It's a branch of mathematics now. And I would like to talk about the origin of this subject because it comes from a very nice problem, which to begin with was an easy problem just because somebody has tried various options, asking that question and didn't leave it. And that's what led to this subject. And I found that very fascinating once I learned about it. So I would like to talk about it. And so for that, let's talk about this specific matrices. These are called circulants. So xi's are variables here. This is n by n matrix. I hope the form of the matrix is clear. So this is x1, x2, x3, so on up to xn. Then xn, x1, x2, xn. This is like cyclic, what you say, right? So xn, then there'll be xn minus 1, so on. And last row is x2, x3, x4, x1. So on the diagonal is x1s. Then on this diagonal just above the main diagonal is x2, 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 so on. And similarly here also you see the diagonal entries are the same. So this matrix is called it's a cyclic matrix, but its determinant is called circulant of order n. Okay, so we will denote this by theta n. So I'll keep this notation throughout the talk, theta n. So for example, let's see an example. So if it was 2, n was 2, then this matrix is nothing but x1, x2, x2, x1. So its determinant is x1 square minus x2 square, right? And for n is equal to 3, one can do the computation and see that it turns out to be this polynomial, right? So now I'm going to think of this theta n as a polynomial in x1, x2, xn variables. And I also keep the coefficients. You can actually, if you see, you can do it coefficients over any field, but I'll be keeping it over C, field of complex numbers. Okay, I'm thinking of theta n as a polynomial, complex polynomial with variables x1, x2, xn. Okay, so this polynomial was studied by Catalan in 1846. So the question that I'm interested in, and I'll be talking throughout certain modifications of this also in this talk, is that what is the decomposition of theta n into irreducible polynomials? Okay, so for example, let's look at examples. Let's look at theta 2, right? We computed it that it's x1 square minus x2 square. Its decomposition into irreducibles is x1 plus x2 into x1 minus x2. Okay, so similarly for theta 3, if you check, it has this decomposition x1 plus x2 plus, just because I wrote it, you can check that it is x1 plus omega x2, where omega is the third primitive root of unity, omega square, and similarly x1 plus omega square x2 plus omega x. So the question is, does theta n factor into linear terms, right? Theta n is a polynomial, and knowing that what is the decomposition of a polynomial into irreducibles gives a lot more information about the polynomial. So the first question that I'm interested in asking is, does theta n factor into linear terms? Okay, that means degree 1 polynomial. So this x1 plus x2 is a degree 1 polynomial in Cx1, x2, xn, right? So that's the question. So this was conjectured by Spottiswoode in 1856, and it was proved by Cremona in 1856. Rather, what Cremona proved was gave exact decomposition of theta n. Not just proved that it is linear, but he also, so actually Spottiswoode had some kind of formula like this, and Cremona proved it. So let's try to understand this formula. So here what he has is, so zeta is primitive nth root of unity. And what he proved is theta n is a product of these linear polynomials. I'm emphasizing the word linear. X1 plus zeta j x2, so on up to zeta n minus 1 j xn. Okay, where j, and this is a product with j goes from 1 to n. Okay, so now this was a result that Cremona proved. Let's see a quick proof of this. Okay, let's define this polynomial with variable in x1, x2, xn and variable t. I'm also attaching another variable. So let's call it ft with x1 plus x2 t plus x3 t square, so on up to xn t to the n minus 1. Okay, I'm thinking of this as a polynomial in t. Okay, with the xi's also are variables, but as a polynomial in t, it's a degree n minus 1 polynomial. And what we want to prove is, if I want to prove Cremona's result, basically I need to prove that theta n is a product of f zeta j, where I'm substituting zeta j for t, product with j goes from 1 to n. Right? This is clear that just proving theta n is product proves the result. Okay, so let's see how do we prove it. So I'll show you the proof for n is equal to 3. General proof is along the same lines. So let's see this, just because we know what is, so just remember what is f1, f2, f3 is. So if you see, if you multiply these two matrices, x1, x2, x3, this one, and you take this polynomial, when you multiply, you really get f1 here, then f zeta square, zeta f zeta, zeta square, f zeta square. This is just a matrix multiplication, and we know explicitly what ft is. Okay, I'm substituting it and I get it. Now, when I want to know the determinant of this right side matrix, so this is, let's look at determinant of this matrix. It's going to be f1, f zeta square comes common, and I'm left with the determinant of this matrix, which is 1, 1, 1, 1 zeta square. We know this matrix, this is a one de Monde matrix, right? And we know that this determinant is non-zero. So when I look at this, now I was interested in determinant of this matrix. Is my cursor visible? Is my cursor visible?
Yes, Pooja.
Yes, yes.
Yeah, so I'm interested in determinant of this matrix, right? So now if I want to know determinant of this, that's going to be determinant of this A3 into determinant of this matrix, which is equal to F1, F zeta square into determinant of this matrix. And just because this determinant is non-zero, what I really obtain is theta 3 is F1, F zeta square, right? And that's what we wanted to prove. So if you remember, this is what we wanted to prove. So this proves Cremona's result. Okay, and one can do now the same argument for n by n case also. And so this is something that was done for these x1's variables. Now let's generalize this problem a little bit. Okay, to generalize this, I'll talk about group determinants. So let's see what's that generalization. So take G to be a finite group, and let's say these elements are, each elements are A1, A2, so on up to AN. And I consider the variables XA1, XA2, XAN. Okay, just that the variables are indexed by the elements of the group. Now consider this matrix BG, which is XA1, A1 inverse. Right, that makes sense because this is a group. So all this A1, A2 inverse makes sense. So this will be another element of the group. So this gives me a matrix, okay? And this matrix, the determinant of this matrix BG is called group determinant of G. Okay, so this is denoted by theta G. I will be denoting this throughout the talk. I'll be calling theta G by determinant of this matrix. Okay, this, remember, it's AI AJ inverse. So that's easy to remember, and then there is an X. Okay, AI AJ inverse are the IGth entry. Now, why do I say that this is a generalization? So let's see that. So for example, if you take cyclic group Z3, and I want to order these elements in an appropriate way. So let's order A1 is 1, A2 is T, A3 is T square. Okay. Then if you do the computation of this matrix, which I said BG, and I'm writing here BG transpose, then it really is XA1, XA2, XA3, XA3, XA1. You can just check that. And what is important here is that So this matrix really corresponds to my A3, right? So this is exactly, if I just change the basis xi to xai, it's the same matrix. I only have to change this xai to xi. But as long as I'm interested only in decomposing the determinant of the matrix, this change doesn't do anything. I just need to replace those variables, nothing else. So in general, for Zn cyclic group, I get theta g is theta n. Theta n was the circulant of order n. And therefore, I know already the decomposition of theta g for G, a cyclic group, that it is this product of linear factors, right? This is the result of Cremona. Now, I know this result for cyclic groups, and this is what we always do, that we are very hungry, right? When we get some result for cyclic groups, we want to know, okay, for what about for any finite group? So that's the natural question. What is the decomposition of theta G for a finite group G? Okay. And now, so for example, let's see some examples. Let's take G to be Z mod 2Z cross Z mod 2Z. Okay. And here I'm putting A1 to be 1. So that makes a little bit difference because as we will write the elements. Okay. So then the determinant, the group determinant is this product of 4 factors, x1 plus x2 plus x3. Any other elements you put one element, you put 2, 3, 4. So that's all I'm doing. Okay, A2, A3, A4. And so this decomposes like this as, again, linear factors. It's surprising, right? So the question is, are factors always linear if I take a finite group? Are factors always distinct? All these are also distinct. If you see, I have not seen any powers of irreducible polynomials. I'm just writing this like this. There are no powers here. These are all distinct so far, whatever we have seen. So for abelian groups, this was proved by Dedekind in 1880 and by Burnside in 1894. Okay, so what, let me tell you Dedekind's result actually. It's very explicit result that he proved. So to do that, let's say G is a finite abelian group, and let G hat, so I fix G hat to be the set of all group homomorphisms from G to C star. Okay, this is called set of characters of the group G. Yes, and what Dedekind proved was that theta G is the which is by definition is determinant of xg H inverse, is, remember there was this product over J goes from 1 to n. Here the product is over all characters of G, and with these are the linear factors. Okay, summation G goes to G, chi G, xg. Is this term clear? So what is theta G? So theta G is, chi is a homomorphism from G to C star. So these are going to be complex coefficients. Okay, these are my variables xg, and this is summation over all elements of G. And then there is a product. So for example, let's look at Z3. Okay, we have done one way of Cremona's proof. We know that Z3 is whatever I have written here on the right. Let's try to check if it matches with Dedekind's formula. Okay, so what are group homomorphisms from Z3 to C star? So Z3 is a cyclic group. The homomorphisms are determined if I know what it does to what it does to the generator. Okay, now, so this is X1 is identity element, and let's say X2 is my generator corresponding to the generator element. A2 is the generator. Then there are only exactly 3 homomorphisms, and that's why what it says, there are 3 factors. That's what the product is. And one homomorphism takes X2 to the element generator to omega. Another homomorphism takes it to omega square, where omega is the primitive cubed root of unity. Okay, so that justifies that it's exactly the same, and hopefully it makes it clear also that how to work with this formula. If there are any questions, please feel free to ask. Okay, so similarly, one can check that for Z2 cross Z2, if you write all the group homomorphisms from Z2 cross Z2, you get this decomposition that I wrote here. So I wrote a decomposition here. You basically get this decomposition just by knowing the group homomorphisms from G to C star. Now, if you think about it, we didn't start with group homomorphism at all, right? It was a question about certain matrix, finding its determinant, finding its decomposition. it didn't look like that we'll come to group homomorphism, but that's kind of a surprise that we came to this simpler problem. It's in finite abelian groups, it's a simple problem to find all the group homomorphisms, just because we know the structure theory, right? Structure theorem for finitely generated abelian groups tells us how to find all characters. Okay, now, so G abelian, I've got this. This is what Dedekind proved. Now, of course, the question is, then next question that he was led to ask, what can I say about the decomposition of theta G for a non-abelian group G? To do that, then he started looking at certain examples. And first non-abelian group is, of course, for us is S3. So he started looking at S3 and what is the result for S3. So let's, to explain you what happens there, I need to order elements in certain way. We have to order, right? I mean, it's a matrix. I need to order elements in certain way. So this is how I'll be ordering the elements of S3. I'm keeping X1 as XE, X2 is X1, 2, 3, 1, 3, 2, 2, 3, 1, 3, 1, 2. If I change it, it just changes the indices and nothing else, but it's good to fix it because then only I can say this explicitly. So then what he realized that for S3, group determinant is a product of polynomials, but now two things fail. So here, if you look at abelian groups, all the factors are linear, right? This is a scalar and all of these are, there is no power here, there is no power of the, and he also showed all of these are distinct. So that's another part that he showed. So there are no powers to the polynomials and all are linear. For S3, both these things failed. So I got some non-linear polynomials here. So this is a non-linear because I see x1 square, x2 square. So it's a degree 2 polynomial. And we also saw a repetition of this polynomial in the decomposition. So this has a here 2. So this polynomial occurs with multiplicity 2 in the decomposition of group determinant. That's another way of saying it. So both of these failed. And that was now, of course, that meant that Dedekind wanted to understand that why it happened. And so the question then he was led to ask, for general finite group G, what are the degrees of irreducible constituents and their powers in the decomposition of theta G, right? So how do I find all the irreducible constituents and their powers? So Dedekind asked his student Frobenius to think about it. So Frobenius was working with Dedekind at that time, and Frobenius in 1896 solved this problem. Okay, so what did he do? He defined what's called representation of a group, and he had to solve. He wanted to solve it, and he also wanted to solve because it should generalize the abelian group results that Dedekind already proved. So this notion of representation of a group generalized the notion of characters of abelian group. So remember, characters were the group homomorphisms from a group to C star. That's what character of an abelian group was. So let me just recall, let me just say some basic definition of representation theory of finite groups. Then I'll tell you what is the result that Frobenius got. So given a finite group G, a representation of G is a homomorphism from G to the set of automorphisms of a finite dimensional complex vector space V. So that is, Phi is a, so this I write as GLV. These are automorphisms of a finite dimensional complex vector space. And group homomorphism would say that phi G1, G2 is phi G1, phi G2. Identity goes to identity, right? So these are the two things that I want for representation. And I need a concept called dimension. So by dimension of a representation, I will mean, I define it to be the dimension of the vector space. I always take finite dimensional. And here also there is something important, which is complex vector spaces. Okay, I'll say something about this complex later, but this is what we mean by dimension of a representation. Okay, now let's see an example. So if I take a group G, then if I take a map G to C star given by phi G is equal to 1 for all G, then this is a representation of a group G, and it has dimension 1. Right? It's a one-dimensional representation of a group G. So for example, let's take Cn to be cyclic group with n elements. This is back to our Z mod 3Z problem. And I take phi to be Cn to C star or homomorphism, then because it's a homomorphism, I should have that phi xn is equal to 1 for all x in the cyclic group Cn, which means the only possible images that I can get are nth roots of unity. Okay, so to understand all the representations is understanding all the one-dimensional homomorphism. So that tells me if A is a generator, then its image should be nth root of unity. Okay, so one can write those, and let me still say a little bit here what I have written here. I'll use this. Okay, so let A be a generator of Cn and zeta n be the nth primitive root of 1. Then phi is completely determined by phi A, right? Because it's a cyclic group. What happens to the generator tells me for any other element. And so suppose phi A is zeta ni, the ith power of zeta n, then we denote this phi by phi I. So just remember this. I'm going to use this notation. So phi I is the ith power. So fix a generator, ith power of the nth root of unity. Okay. Now, so these were examples I gave you for representation. These were one-dimensional representations, right? This is C star. So that's GL1C. This is also GL1C, or one automorphisms of a one-dimensional complex vector space. Let's see some representations of higher dimension. So for example, if I take, I'm defining this map from S3 to GL3C, where I explicitly give you the matrices, okay? I leave it for you to check that phi actually is a group homomorphism. So this gives me a representation of S3, and it is a three-dimensional representation of S3. So dimension of this representation is 3. Okay, so now I also need some more concepts to state Frobenius result. So given a representation phi from G to GLV, a subspace W contained in V is called subrepresentation if phi G W is equal to W for all G in G. That means W is G invariant. So if I take a G, action of G on W takes it to W. Okay, and I say a representation is irreducible if it has no subrepresentation, no proper subrepresentation. Okay, what I mean is there does not exist a W which is not equal to 0, not equal to V, and is a subrepresentation. That doesn't happen. So any subrepresentation of V has to be only 0 or V. Then I say V is an irreducible representation. Okay. And for example, one-dimensional representations are irreducible. I cannot have a sub-representation in between. Dimension is just 1. Anything proper subspace is going to be 0-dimensional. So nothing else is possible. So this is irreducible. I need this notion, word irreducible representation. I'll be using it while stating the result. And another thing I need is equivalence. So two representations. So let's call phi1 v1. By phi1 v1, I mean this is the GL v1. It's a map phi1 from G to GL v1. And phi2 is a map from G to GL v2. So I said two representations, phi1 v1 and phi2 v2 are said to be equivalent if there exists an isomorphism T from V1 to V2. So this is, look at this diagram, so that probably is more clear. V1 to V2, I have a T such that this diagram commutes, which really means that if I follow this path or I follow this path, I get the same value. Right? So T P1G, so that's P, I get P1G, then T is equal to T P2G. I see a question, so maybe let me answer this. Is the subspace,
Okay.
yeah. Is it okay if I answer this question now itself?
Yeah, sure. It's up to you.
Is the subspace W?
Yeah, go ahead, Pooja. That's what I was pointing.
Okay. Is the subspace W sub-representation, or is phi restricted to W a sub-representation? So see, W, the action on W is only via phi. Then I say sub-representation. Okay, so it is, if you look at the definition, this is phi G. The action of G on W is via phi. Does that answer this question? I mean, as a subspace, I cannot say that there is an action or not. It is like a restriction action of phi on the subspace. And whether it is an action or not, that's important. Yes, so that's the second part of what you have written. That's correct. Let's see now.
Question. I thought that I should ask it now.
Okay. See,
Yeah, wondering that this fee from G to GLV, what does it actually captures? I mean, for G. I mean, I was just wondering that for group, what does it captures? I mean,
So,
what information we want to capture?
About G, you mean?
Yeah, about the group. So via this fee, the whatever fee you were taking,
Yes.
what trying to capture?
Okay.
What
It is, see, think of this. GLV is like set of matrices, right? I mean, that's, V is a finite dimensional vector space. So let's say N, this is really GL and C. So what it gives me the information is that it relates. So G has certain group law. And I'm able to take every element G to a matrix, and I'm able to do certain computations with matrices. And many a times I get information about G, but you know, working with G may be difficult, but working with matrices is sometimes very easy. So that is the information I'm trying to gain, but it may not be complete, right? Because it may not be an injective map. So therefore I have to worry with about different fields. Does that answer your question, Ratna?
Definitely. Thank you. Thank you very much. Yeah.
Okay, so this is okay about equivalence of representations? I mean, even if it's not clear, it's fine. Just remember that there is such notion which relates to representations. And if I can, so I just need it in my thing, and you can come back and look at it later also after, if you are seeing this for the first time. Okay? Now, so for example, let me give you an example just to make the point clear. And so let's look at these two representations. Let's say phi1 from S2. S2 is a cyclic group generated by two elements, generated by 1, 2. Okay, S2. So S2 to GL2C. I'm thinking of this as generated by 1, 2. Okay, cycle 1. Then consider this map. One has to go to identity. It's a group homomorphism. I don't have any option. I take 1, 2 to 0, 1, 1, 0. And it is a group homomorphism. Similarly, I take phi2. Where 1 goes to 1, 0, 0, 1, again, just identity, and 1, 2 goes to 1, 0, 0, minus 1. Right? These are two different group homomorphisms, or in my language, these are two different representations of dimension 2 of the group S2. Okay, these are two-dimensional because of this GL2C. Okay, now I want to claim that this phi1 is equivalent to phi2. Okay, and I mean, I'm not going back to the definition, but I'm just saying that the equivalence here would mean that, so, okay, look, maybe I can say a little bit. So this really means T is invertible. I can bring this T here. Okay, so that would say T inverse phi2G, T should be phi1G for all G in G. Now, if this G is identity, anyways, it is satisfied, right? If G is identity, this is identity matrix, this side is identity, there is nothing to worry. In this case, the only non-identity element is this 1, 2. So the equivalence of this really follows because I can find this matrix X given by 1, 1, 1 minus 1, which conjugates this matrix to this matrix. And one can check that the definition would imply that these two representations are equivalent representations. Okay. Let me give you also a non-equivalent example, just to keep it in mind that not everything is equivalent of the same dimension. Okay? So, I mean, so I should also point out, if two representations do not have the same dimension, there is no possibility of their equivalence, right? Because T has to be an isomorphism, which means dimension of V1 is equal to dimension of V2. That's important. Now, let's see. So for this cyclic group, I didn't remember we defined this phi I and phi j. Phi I A is zeta and I, and phi j A is zeta and j. And so claim is if I is not equal to j, then phi I is not equivalent to phi j. Okay, which really means in this case it's one dimensional. Isomorphism means multiplication by lambda, right? Linear space to linear. So there is no lambda such that lambda zeta n I is equal to zeta n j lambda for I not equal to j, right? I mean, in this case, you can just kill lambda and that would say zeta n I equal to zeta n j would imply I must be equal to j. So all of these are inequivalent representations. Remember this, we are going to relate it with something, a Dedekind proof. Okay, we'll try to bring that. So some result that Dedekind, we have seen Dedekind's result, but in a different language. So now let's see what Frobenius proved. Frobenius' result was the following. So remember Dedekind gave Frobenius this problem to look at, and this is where what Frobenius came to. He defined the notion of representation, defined the notion of equivalence, defined the notion of subrepresentation, and I mean all that he did. And then he also proved some more results. He proved that if I take the set of all inequivalent irreducible representations of G, okay, it turns out that this is a finite, it's a finite set. So I call it, given a G finite, then set of all inequivalent irreducible representations of G is a finite set. So let's say it is rho 1, rho 2, rho k. Then what he proved that the group determinant of G is product over all irreducible. Now these are all irreducible representations of G. And here you have the determinant of summation xg rho G. Now these rho G's are matrices. Okay, these rho G's can be higher dimensional matrices. So with G varying over G, and the power is dimension of rho. Okay, so let's look at it once more, whether we understand all the terms. So the product is over all irreducible representations of G. And then these are like determinants, where for each row, you look at this. This is going to be a matrix, which means this polynomial, if a row has dimension greater than 1, then this is not going to be a linear polynomial, right? It's going to be a polynomial of degree greater than equal to 2, depending on the dimension. Whatever is the dimension, that's what you are going to see. And then there is a dimension row. Is that okay? And whatever is the dimension, you see even the multiplicity. That's something very nice. He gave, and all these are irreducible. So that's important. He said these are irreducible. Okay, so he gave all irreducible constituents with their multiplicities, the complete answer to that problem. Okay, so just comparing this result with what Dedekind proved, for G abelian, set of irreducible representations is nothing but set of characters of G. Okay, and in that case, this rho G, because these are characters, so these are one dimensional, so these are scalars. So I can really write scalars on this side. So I wrote scalars here. This is chi G, and I call these chi's. This is product over all characters, summation chi G x G. This is now linear, right? All these are linear factors, distinct factors, and numbers are exactly, this result is exactly matching with the result that Dedekind proved. Right? This Frobenius result generalizes Dedekind's result. Is that okay? So if there are any questions, please feel free to interrupt me, okay? So now let me, so what I want to do in next few minutes is just show you what I said about S3, okay? And then I'll leave this question. So I said for S3, the decomposition of group determinant is this, okay? Let's try to justify that. So this is theta S3. So what I'm really saying, if I, so this has 4 components. One component occurs with multiplicity 2, other 2 are multiplicity 1, and this component has degree 2. Let's try to justify. Can we justify that? Okay. Now, of course, I'm going to assume certain things here, some information, but not much. Okay. So one thing that I'm going to assume, so okay, let's define. I am going to tell you all irreducible representations of S3, okay? Because I need that. I tell you irreducible representations of S3 are rho 1, rho 2, rho 3, and where I tell you what is rho 1, what is rho 2, what's rho 3. We will substitute and check whether this works or not. So rho 1 is the identity trivial representations, or what's called identity representation. What it does, it takes every element G to 1. Okay, so this will give me the term x1 plus x2. So what do I mean by term? I mean is this term. So I'm looking at now this term, which is a summation xg rho g. So rho g is 1 for all g. So this summation is going to be just x1 plus x2 plus x3 plus x4 plus x5 plus x6. Okay, that's going to be my factor coming via for the representation rho 1. Let's call it phi1. This is this factor, right? It's this factor. Now let's write another rho 2. Rho 2 is a group homomorphism of S3, which we call it sign representation. You must have seen that. So what it does is it takes transpositions to -1, and identity goes to 1, and these 3 cycles go to 1. Okay, this is again a group homomorphism, and if you look at, you substitute in summation xi's, then okay, there is something missing here. I think this dot did not compile. So here I have written x4, x5, x6 for transpositions. Okay, x2, x3 are 3 cycles, and x1 is the identity element. So that's what I have used. I think probably I didn't compile it and it has not come here. So this is x1 plus x2 plus x3 because of this 1 for all 3 elements. And the -1 comes because of this. This is my another linear factor, which is here, right? So this is x1 plus x2 plus x3 minus x4 minus x5 minus x6. So that's because of this. Now let's look at another one. So if I look at now Frobenius result, again, if I want to have a degree 2 factor, which means I must have a 2-dimensional irreducible representation, right? I must have that. So let's see that. Now, rho 3, I'm giving you the representation really. I'm giving you the representation here. So it is S3 to GL2C, which is takes identity element to the identity matrix. 1, 2 goes to 0, 1, 1, 0. Similarly, 1, 3. I've written the matrices here. Of course, that means that I know something how to do that. And I'm not, there are 2 things I'm leaving out. One, it's a group homomorphism. Second thing I'm leaving out that it is an irreducible representation. These are not very difficult, okay? Once one goes to the definition, it can be done. Then this term, so let's go back to, the reason I'm writing it here is because I want to tell you how to think of this term, okay? So this is summation xj rho g, okay? So let's see what it becomes for us. So this is xg rho g, right? So this is rho e. I'm calling this as x1. So that's x1 here and x1. And my x2 is this one, 3 cycle. So that's minus x2 here, minus x2 here. Here I have x2 and I have no x2 here, right? 0 with a 0 coefficient. Similarly, this is with x3. So that's x3 here, minus x3, minus x3, and so on. So that's how one gets a matrix. So this is a 2 by 2 matrix. Okay. So you can see that if rho was a n-dimensional, this will be like a n by n matrix, right? So what the term becomes is determinant of this matrix, and that will be my phi3. And that if one does the computation, it agrees with so it agrees with this term. If one writes the determinant, one gets basically this term. And then by Frobenius result, I should have phi s3 is phi1, phi2, phi3 square. Okay, and nothing else. And so, so now once I've got it, for this justified what Dedekind gave to Frobenius. Dedekind had the expression for S3, and Frobenius with his general method could do it. But now this already opened up many more questions, right? So this, we have done it for S3. Now question is that if I want to know the group determinant for a general finite group, then the question that I need to ask is, what are all the finite dimensional, inequivalent, irreducible, complex representations of a given finite group G? Right? That's a question that's not answered for all groups here. It's only done for S3. But if you want to know group determinant for any group, you have to answer this question. And I should say this question is still very much open. I mean, we don't know the representations of finite groups, even P groups. We don't know the P groups, one doesn't know even classification. So of course, representations, one doesn't know. But many, many nice groups also, we don't know the representations. So that this became as the beginning of the representation theory of finite groups. Of course, it has taken many more directions. This is not the reason why people study representation theory of finite groups, but this was the beginning. Okay, so yeah, I think I'll stop at this point.
Okay, thank you, Pooja. Let's thank the speaker. So, Pooja, there is one question in the chat.
Yes. Okay. How do we get the matrices where the elements of S3 to be mapped? So this is a question by Milton Saha. Yes. Okay. Let's go back there. That's what I meant by saying that it is a hard question. Okay. Given a group G, knowing these matrices is really, when I am writing this here, I'm really using some more information. It is not obvious because GL2C is an infinite group, right? In particular, I can put various kind of possibilities. So here, what I have used here is, I should tell you what I have used here. Okay? I have used something here. I go back to some representation here. So somewhere this representation has helped me in writing those. Okay, so this is what is called this is a three-dimensional representation. It has a sub-representation of dimension 2, which I know it cannot be. I mean, one can show that it does not have all sub-representation can't be one-dimensional for this representation. This is like where general theory comes in. Okay, that's where I'm hiding that in the carpet, under the carpet. And it has a certain sub-representation of dimension 2. And what I have written here is really finding that sub-representation. Okay, I found that sub-representation and written those matrices. But yes, it is not easy to find always. Yes, it's S3, so I could do it. Somebody else also has asked, so I think this question by Aditya, if we know the group determinant of a group G, can we say something about the group determinant of a group that contains G? If we know the group determinant of a group G, it's okay, let's see. Maybe in certain cases, but not always. Okay. So for example, it will depend on so for example, if I have a complement, some constituents you can say, so for example, if a bigger group, let's say I have a H contained in G, such that G is H cross K, okay, and you do know the group determinant of H, then you can say something about group determinant of G also, something, but not complete information, because for that you need to know the K also. But it may not be always possible, okay? In certain cases, if it's a semi-direct product, maybe you can say, not always. Yeah, it's not.
Any more questions?
Yeah, Pooja, I wanted to ask you one thing. First of all, it's a very nice talk. That here, we have seen that we start with a finite abelian group, and then we are going to define it for the finite non-abelian group. So, can we try similar kind of thing for finite semi-group?
What do you mean by semi-groups are finite?
Yeah, I'm taking a
you mean yeah, that you don't have the full group property, you only have the composition. You only have the composition. Of course, all that makes sense. That's not a problem. And
like here you are saying that determinant. So I wanted to know that whether such kind of things.
That's an interesting question. But even for semi-groups, people talk about representations, right? Although semi-simplicity and all you don't have. So it is because you can talk about group algebras. So if you have a semi-simplicity of group algebra, so then I believe it will work, because somehow that is what is used in the proof. And I can mention you more things about it, but it is what I've used is in the proof. I mean, what I've seen in the proof is semi-simplicity of group algebra. And for your semi-group, if you have that kind of property, then it should be okay, I guess. But I'll check more details and let you know.
Okay.
Yeah.
Okay. Thank you.
Any more questions?
So Pooja, I have one question. So for this group G, you are mapping to GLNC. So which N to choose? I mean, or is there, I mean, which N will be the appropriate N, or is there any upper bound which is useful?
So there
For
are
a-
options, yes. And anything else? Is there, so question is about which N, how do I know anything about N? Do I know anything about N? Is probably the question, right? That you're asking. Okay, so for finite groups, this is known that if you have these, so I wrote this set representations. I wrote rho 1, rho 2, rho k as a set of all irreducible, inequivalent irreducible representations. So suppose rho 1 has dimension n1, rho 2 has dimension n2, and so on up to rho k. Okay, we know certain things about this. So this dimension divides the order of G. So that means you can't have very big dimensions. First thing that. Second thing, you know, summation ni square is the order of G.
Okay.
So let's say if rho 1 has dimension n1, rho 2 has dimension n2, then I should have this, I mean, that's classical and known, a summation ni square is order of G. So that also gives you lots of, so for example, S3, once I gave you two one-dimensional, and another thing you know is the number of irreducibles is number of conjugacy classes. So for S3, this is kind of enough information for me to know that there are going to be exactly 3 irreducible representations. And once I gave you two one-dimensional, I mean, it has to have two one-dimensional and one two-dimensional. There was no other possibility of satisfying all that. Okay, so for small groups, one can actually do this numerics and find out. But then otherwise, one needs to use certain more tools to figure out. But once you have summation ni square is order of G, you know it's complete. You don't have to worry.
Thanks.
Yeah, there is a full way to determine those.
What do you mean by full way to determine those?
This formula you mentioned, that summation ni square and equals to cardinality of G. That, and I don't remember one more result that they, at least for most of the groups, I think one can, for small order groups, at least one can get all the
Small
possible.
order. But
Yeah.
Small order one can. But for higher groups, we even still don't know. We still don't know.
Sorry?
For higher order groups, we still don't know these NIs. Right?
Oh, so getting all the NIs, it is still.
Yes.
Okay.
May I just add to it?
Yes, Nanda, please go ahead.
Hi, Pooja.
Hi.
So very nice talk, and I always enjoy listening to you. You present in a very lucid manner. That's what I like about your talk. So regarding this small groups, so I did this as a small exercise for computing everything without going into high results. So you'll be able to find a group of order as small as 24 or 22. I mean, it's not greater than 25 for sure, where these will not suffice, where you will be able to have two possibilities of NIs using summation NI square and everything. So bigger tools need to be brought into picture for these things. That was just a small comment about it.
Yes, I agree with what Sugandha is saying, that this summation ni square equal to order of G and ni dividing order of G, that is very less of information. That's very less of information.
So
just
Pooja,
as a curiosity, I did this exercise to, get what is the smallest order where it fails. And it was something like a small, lesser than 25. Yes.
So in fact, Pooja, what I was saying, that taking this tensor product, alternating products of smaller, suppose you determine some representation, use their tensor product, their alternating product, they will give some more, and then one can check if they are non-isomorphic or not. So does that go quite far, or even that also doesn't go quite far?
So the problem is that tensor product and all may not be irreducible, right? See, I am interested only in the irreducible representations. You can
Yes.
something, but then you need to find their constituents, and that may be hard, right?
Okay, so you are saying that even including those techniques also, it doesn't go very far. Okay. So there is one more question in chat box, but I also had one thing. Actually, this was the question which Ratna asked at the very beginning, I think.
Okay.
I think her question was that this fee from G to GLB, that what does it tell about G?
Yes.
Maybe you can say that at least in your talk itself, we saw that it factorizes that circulant of G. using information on these fees, you get a factorization of circulant of G.
That's correct.
So there is one more question. So yeah, if you want to say something on that, or there is a question in chat box, please.
Okay, let's see what question it is, and then we can come back to that question if we need more details. But I don't see that.
Varun Sa, once we factorize the group determinant of G, can we determine the irreducible representation of G just from the factors?
Okay, that's a good question. See, if you can factorize, you will get this information. How many irreducible representations? So this is the Frobenius result, right? And what he also proved is that, I mean, once you can do it, you know how many irreducibles are there and what are their dimensions, right? So now it is up to you whether that is good enough information, but for representation, you mean really knowing group homomorphisms. You will not have that information, right? So because you see, this is oh wait, let me, because see, it is like you have done a determinant. I mean, you have taken determinant. I mean, can you go back once you know a determinant of a matrix? Can you go back to that original matrix? Is the question. Right? So what I'm saying here, if you know this, for example, S3, could you guess that this is going to be my group? That's very hard. I mean, I don't think you can go back this way, but one dimensionals you can. One dimensional you can do that. So does that answer the question?
We have time. Can I ask something?
So there are a few more questions in chat box, I guess. One Milton, and then I think Sugandha wants to ask something.
Sure, please.
So Milton has a question: up to what order of this complete classification is known? Up to what order of the groups? Up to what order of groups is this complete classification of irreducible representations completely available in literature? So actually, if you talk about order, I think that maybe Sugandha may be able to know that because Sugandha works with this computational aspects, but it may not be very far, right? One doesn't do actually with respect to order because groups do get very complicated. What one does is classifies groups into different types. For example, if you look at Sn, okay, Sn has order n factorial. However, just because this is a nice group, you know all representations of Sn.
It's 11 o'clock.
And similarly, you do finite groups of Lie type. You kind of classify groups in different types. And certain of those types, even if they have high order, you can understand that. So usually, but I think computational aspect, I don't know exactly, but I think it may not go beyond like a couple of hundreds order if you want to know exactly for all groups. That may not be, it takes lots of work. I mean, computational data, it takes lots of computational data to find those matrices exactly. And the numbers get quite huge soon. So, yeah.
So, okay, maybe we can take one more question from Sugandha. She had something to say.
Yes.
And
just maybe something apart from representation theory. So group determinants is what we begin with. Are you aware of the applications of group determinants independently? Asking just in order to understand more of impact of representation theory.
Actually, group determinants, I think this come in number theory. That I know. But okay, I don't know exactly. But so, for example, Dedekind, the reason Dedekind came to group determinant was because he was interested in certain number theory questions. He wanted to understand certain extensions, field extensions, and how their behavior is. But I am not aware. I mean, as of now, nobody talks about group determinants as such. Everybody has forgotten and they just talk about representation theory, right? So nobody talks about group determinants per se about this. But
even I did not hear recently. So that was just curiosity, which just came out of this thing when I saw this. Yeah.
No, it's very I mean, I think number theory has applications. They may be able to say something more about it. Dedekind came to this question because of number theory. He wanted to understand certain extensions, but yes. I don't know other applications.
Thank you.
So there are some more questions, but maybe I think we can. So I will request, please write it to Pooja directly because it's already 11:02, and we have to start the next talk. So once again, let us thank Pooja for a nice talk. Thank you, Pooja.